Well, hi, and thanks so much for joining me here in my shop. It's been a few days since I've been in here, busy doing other things with my family, but I'm back in here today, pretty happy to carry on with this fantastic radio. So it's given me a few days to think about the situation here. Let me just fly in here for a closer look. I think the next thing I want to do with this is take a look at this particular capacitor. It's the one in the metal can right here. And make some decisions around whether I should do anything about this, whether I should attempt to replace it or determine its quality or something like that. This capacitor I think is worth poking around with. Really don't know for sure what I'm going to find out with it. When I do that, let's just take a close look at it to start with. So now that I'm taking a close look at it, I'm getting cold feet here. There's a lot of wires connected to it. That makes I have to disconnect the wires, I believe, to test this properly. Just take a look. It's a metal can with tabs. See the tabs around the side there? You can pry those tabs. I pull the guts out if you want it. That's not my intention at all. Boy, how could you test this? Now, there's a chance that these wires actually don't go anywhere. Fat chance on that. There's a lot of them. But for instance, they may be going to open tube elements and stuff like that. So it may be possible to test this capacitor, but they're just sitting right where it is. I have to look at the schematic a little bit. The other thing is, what is this capacitor doing in here? Why isn't it just another one of these? Why is it this can here? And I know the answer. The answer is this is a fairly large capacitor. Probably a 0.1 or maybe even a 1 microfarad in here. I'm pretty sure when we look at the schematic, which we're going to do in a minute, we'll find out that this guy's job is basically to drain out RF from circuits where you don't want it, and to drain it into the chassis, so to speak. That's really not how electricity works, but we can put it that way. So that being the case, and this is at a radio frequency, I'm pretty sure this has to get rid of radio frequency signals that the radio doesn't want where they are. So that, as I understand it, that's why this is not electrolytic. This probably isn't electrolytic because it was more expensive to produce an electrolytic capacitor in this position. I don't think this is electrolytic. Kind of looks like it, but I don't think it is. So let's look on the schematic, see what we can find out there before I say more things that are dumb. Okay, so just before we flip over to the schematic, there's another thing about this radio I've been curious about the entire time since I've noticed it, and I really want to pursue it a little more. And that's this guy here. What is going on with this ring, these wheels, these adjustments? There is something going on here. Surely to goodness these just aren't stabilizing this wheel into a position, are they? Is that what's going on here? I don't know. There's something going on with all this though, for sure. If these were just stabilizing, there'd be another two over here to kind of balance this out. There's something going on. Look, there's one here, one here. There's four of them for the 4 stages. Something going on there I haven't discovered yet. So I've been curious about that the whole time. So let's take a look at the diagram here. We're going to get a chance to find out what those little screws are about. So I've already noticed. Here we go. Okay, so this is a top-down view similar to what we were just looking at. And the capacitor we're interested in is sitting right here. You see the 3 terminals on it, and it's part number 10. Part number 10 is bypass condenser 3 of 0.25. Now I may have 0.25 capacitors here each, so they're not quite as big as I thought. I thought this was going to be a 1. 0.25. Okay, that's good, I think. So, why even think about it too much further? I should just replace them and be done with it. I think that's what's going to happen there, I think. And now, because we have a chance, looking at this wheel, there's one set of those screws, and it's pointed to by 9, and let's see, 8 is pointing at this, I don't know what that is, and then 6 is pointing at the center. Okay, so 987. So 9 is the cam adjusting screw. Screw, should be screws, shouldn't it? Cam adjusting screws. Cam tuning condenser spring. I didn't notice the spring. Screw nut lock washer. Number 7. I'm just taking advantage of my opportunity here to look at this stuff. Oh, 7 is there. This is 6. 7 is what? What? Screw lock. Oh no, it's just listing what it is. Screw nut lock washer. Okay, that's nothing. That's nothing to look at. Number 6. Nut and lock washer. Okay, that's not much more exciting. Nut and lock washer. What was number 8? Again, what is that? 8. Tuning condenser spring. Okay, I'm going to take a look for that. I don't know what that is. Tuning condenser spring. Isn't that set of springs on the other side we were looking at? And what about this capacitor? We're looking at it. Might as well see what it says. It looks like it's being pointed at with two things. 6. Is it 18 and 17? 18 and 7. Looks like there's a resistor. Oh yeah, there is. Oh wait a minute. There's 2 capacitors. There's one here and one here. This one has a resistor across it. So it's 16, 17, and 18. 16. A rivet. Oh, for crying out loud. Grid leak resistor. Grid leak condenser. So that's what those 2 are. And there is one more resistor over here. Might as well take a look at it. 40. It says 46, I'm pretty sure. 46. Intended choke coil. Is that what that is? 46. 46. There is. Well, that's a coil there. That's. The part layout in my radio is different than this diagram. Wait a minute, I'm just getting a little confused here. Tube. Sorry for dragging you through this. So, this part here, I don't think it exists in my radio. Oh, it does. It's just in a different position. It's way back up in here. Okay, enough of that. Let's stay focused on what we're on. I can go on for another hour looking at these little bits and pieces. Back to what we're focused on. This capacitor. So we know now that this is the only 3-part capacitor in this whole radio. So this has to be at 3 of 0.25. And that has to be a schematic in here somewhere. Oh, these are nice. Okay, nicer diagram. Bypass capacitor, showing the wiring here. Excellent. So we'll look on this. I think I know where we're going to find this guy. So here we have a C7, C7, C7 3.25. So that's it. So it's here, and another C7 shows up over here. They're essentially all doing the same kind of thing. They are trying to drain the RF out of, in this case, out of the heater line. And they're showing it here in the radio. You know, they could put this capacitor, they could show it schematically anywhere on these lines. They could show it down here if they wanted. It's shown out here because I think physically it is located near the first tube, and its main job is to quiet down this, because whatever's happening in this first tube just gets amplified more and more and more. So if you've got a little bit of nonsense going on in here, you're going to get a lot of it up here. A little bit of nonsense here won't get boosted much. Nonsense being inappropriate signals traveling through these wires here. So that's this guy's job. And it's just taking the RF and shoving it to ground. Now this is an interesting issue here for me because 0.25. Well, I'm gonna okay. Well, I'm gonna have to explain what I just said. When I first came in here, I thought these were going to be 1 microfarad. So with 1 microfarad, the replacements I have are electrolytic. So I was thinking I'll put electrolytic in here. But electrolytic capacitors are not so good at RF at higher frequencies. So I had a whole plan in mind for how to get around it and examine this issue. But I shouldn't even mention it because these are only 0.25s. And I could probably do that. And we'll check in a minute. So that's what they're so. Now, as for reading these, clearly, well, if I pull this tube out, these wires go open. Likewise, I pull out all these tubes, these wires go open. And if I pull out this plug, they go open down here. So basically, this capacitor would then be, these capacitors would be across open wires. I wouldn't have to pull this tube, and these ones are all fed differently. So it's just all the 26s in the radio come out. Out they come, and then I can test this. This one, let's see, can we test this in place? So one side's to the chassis, the other side is going all over the place. Oh, smokes. But ultimately all over the place, maybe nowhere. Dead. Open. I have the feeling I can just test this one right where it's sitting. And there may be more capacitors along the way here. There's all kinds of stuff. All kinds of stuff. But I think from a test point of view, this looks like it's all open. Especially if I pulled these tubes out, it's just that much more open. I think I can test this one. I can test all 3 of these if I pull these tubes out and I have to pull this plug out for sure. So let's do that. Okay, sounds good. So that's the guy we are going to test here. Pull out all the tubes first. Is there anything else I should do? There's no reason to operate this. One tube we can leave in this guy. Now what do we expect with this capacitor? Do we expect to get a test of this that's absolutely certain? I have to pull this plug out of here too. Well, that's often the problem with doing these things. You can get a test result and then scratch your head as to whether it's really valid. So just for fun and because it's so easy to do, let's just start with this. Connect one lead to ground, or the can in fact, and the other lead goes on any one of these. Let's pick this lower one first. Capacitor. So it says 3.5 microfarads. 3.5 microfarads. It's supposed to be, actually says 3,500 nanofarads. So 3.5 ESR5, 18% loss. I mean, this to me this is all saying really old and worn out. Let's try this. (32 picofarads). It's kind of not really what you expect to see there. And the last one. So when I'm doing these tests, boy, there are question marks around everything. I see the result. I may repeat it on my video, but in my head, it's just big question marks around it all. 34 picofarad again. That would sound like it's open circuit inside there. The capacitor is made up of just the leads. The actual capacitive elements, you know, the foil that's likely in here. Maybe it's disconnected. So that's interesting. Is that really valid? There, see, there I am. So now, I should check to see if I really have replacements capacitors. Let me check and just see. Well, maybe it's good that I babbled about using an electrolytic capacitor in place of this, because I don't have any stock of 0.25 microfarad non-electrolytic capacitors. So either I'm stuck at this point, can't do anything about this until I order those, or we take a shot at using electrolytic here. Now, why wouldn't they use electrolytic here to start with? It's 1929, and it could be making an electrolytic capacitor that would do this job would be far more expensive than doing this. That's my guess. But I have heard electrolytic capacitors are bad at RF frequencies, and there's no doubt this guy's job is up at RF frequencies. So the little experiment I devised in my head, I am now going to set up, and we're going to find out if electrolytic capacitor really does have a bad RF characteristic to it. At least I hope to find out. Let me get it all set up here and we'll see what happens. Okay, well, I think I've got this working the way I want it already. It turned out to be, you know, most of my experiments really flop. Maybe not this one. So ignore all that stuff. There's just the capacitor here and a resistor here. A little hard to see. This is a 250 ohm resistor, and this is a 1 microfarad electrolytic capacitor. They're just in series on this board. So one terminal end of the circuit is here and the other end's up here. You see these two black leads. One is from the scope and the other is from the signal generator that's running here, the sweep generator that's running right here. The sweep generator is sweeping from, I think, about 3,000 hertz up to, let's check, from about 3,000 hertz up to just over 1 million hertz. Okay, it's sweeping now, and the sweep is visible on the scope. There's a few weird anomalies here, which I'm gonna try to ignore. So first, let me stop the sweep. Let's start the sweep. Stop this. Put this in the center. And I see what the problem was. No, wrong way. Okay. Just a little bit bigger. Sorry about this. So I want this sweep to be centered there. So the sweep is going from here right to this edge. It's going from 3 kilohertz up to just over 1 million on here. And so as you go across, the frequency is going up. That's a whole scheme here. The vertical part is going to be coming from the circuit. They put in a carbon resistor and another. I have another carbon resistor. I have two of them here. I can use one or the other. One is a very large resistance. This is 27,000 ohms, and the other is a very small resistance. This one is 150 ohms. The capacitor I have in here is the 1 microfarad electrolytic capacitor. The signal is being applied across right now this resistor and the capacitor, and we're looking at on the scope what is happening on the resistor. Let's take a look and we'll see what we can see. And I'm not promising you this is absolutely clear. So right now the sweep is going from essentially 25 hertz or somewhere way down low up to around 10 kilohertz. This is kind of an audio frequency range here. And what you see is all the voltage dropping across the resistor except out here. So it's just hard to imagine what's really happening right in this area here. Let me just expand it. So it's a little tricky to see. But I would say the whole signal is here, but over here it's not. Now, what frequency are we talking about here? So this is something like almost 0, and this is 100 hertz now. So we're talking about very low. So that's 100, that's 0, that's 50 in the middle. So you can see how 60 cycles would apply to this capacitor in this particular circuit. This is with the high resistance resistor on that we're looking across. But it's definitely got a roll off, like all capacitors do. As the frequency goes down, there comes a point where the capacitive the reactance increases, and it gets, in this case, because of the way I have the test jig, gets up similar to the amount of resistance we're reading across. So I'm going to put a much smaller resistor on now, in the sense that we're going to look, as soon as I figure out what I'm doing here, make sure I do this right. So this is the small resistor now. Okay, so we haven't got much voltage drop to look at. Wait a minute. Wait, no, this should be okay. Not much voltage drop to look at. So I made my scope more sensitive so we can see it here. Have I got this right? Let me just make absolutely sure. Yeah, that's across the resistor. So again, this is roughly very, very low frequency, call it 0, and up here we're at about 100 hertz. Let me center this just a wee bit better. So if that's 100 and that's roughly 0, this is roughly 50. So you can see right in the 60, 50, 60 hertz area, this capacitor seems to, its impedance seems to come down quite a bit. Now what's happening up at the other end? Let's go up in frequency here. Oh my gosh, look at that. So now this is 1000 hertz. So we can see much more clearly what's going on. So with a small resistor there, you got to get all the way up to here before the capacitor starts looking pretty much like a short circuit. And what is here? So this is now 1000. This is 1000 hertz. This is just back from 1000. This is roughly, I think this is 10. 1, 2, 3, 4, 5, yeah, 10. So you come back, you can literally just call this 900, 800, 700, yeah. So around a kilohertz with this particular circuit arrangement. So 60 hertz is way back here somewhere. Let me put the big resistor back on. We'll see how it looks. Okay, a lot more signal, of course. The situation looks entirely different now. It's kind of curious what's going on here. I don't know why it's doing that loping thing, just some fact of how I have the equipment arranged. So again, we're up here, we're at 1000 hertz, and you can see just about all the voltages on the resistor. There's something kind of, maybe there's a hum in there or something like that that's causing this weirdness. Won't worry about that. So let's do this. Okay, so this is now 100 hertz, and almost all of it is on the resistor. Not too surprising, it's a bigger resistor. So let's go up to the high frequency situation here. Okay, so now we really changed things. This is now 5 megahertz up here. This funny little curve right above my finger there. What's that little divot? That's real. I don't know what that would be. That's kind of a funny looking thing. Anyway, small stuff fascinates me immediately. Well, what we see is a roll-off going down. And what's happening here is, this is what I wanted to see. This is the case where the capacitor does not present zero impedance to the frequency that's being applied to it. And that's starting, right out in this area somewhere. You can start to see it neck down. That's with the big resistor. If I put the small resistor on there, okay, small resistor again, we just kind of lost a lot of the signal. Whoops, wrong way. So now we see this actually looks to me to be getting wider and then coming in very little bit. I can't get this any higher than 5 megahertz with my particular signal generator I'm using, sweep generator. So you can still see the roll off out here. This would be roughly 2 megahertz or something, but it's not much of a roll off. So this is saying under this arrangement, most of the voltage is falling on the resistor right in here. As you go forward, more and more starts falling on the capacitor. Again, up around 2 megahertz. So why? Well, and this is with the low value resistor. This is like a capacitor working against a low impedance circuit. You can look at it that way. And there's something funny here. Let's expand this thing way out and look at this thing. So again, this is 1K now. Let me put it up. So this is 10K. So this is maybe 2,000 hertz right around here. So this is kind of odd to look at, because I always think of electrolytic capacitors as being, really powerful capacitors. I don't think much about their low end impedance being bad, low frequency impedance. Again, this is a voltage divider, so it depends what size resistor you've got in there all the time. But I would have just imagined that this thing would not, like this rolling off shows the capacitor has a voltage drop across it, all the way up to, up in this range, which on here would be 10K, 10, 9, 8, 7, 6, 5, 4, 3, 2. So somewhere around 1 or 2K, way above 60 cycles. Let me switch to the big resistor now. I think we'll see quite a difference here. And not only more signal, but now you see that 10K is still here, and all of it, pretty much all of it, is on the resistor the whole time. And that's showing the relative impedance of the resistor and the capacitor is the difference is very great. The resistor is much larger resistance than the capacitor is presenting, so all the voltage is on here. So I guess then the answer to this question, can you use an electrolytic capacitor to drain out RF in a radio like this? RF being only the AM radio band, so we're talking up to about 2 megahertz, in fact, just below 2 megahertz. It's very dependent upon the impedance of the circuit that the capacitor is working against. Now, and what is that? Well, stretching my brain a little bit here, since 2 of these are hooked up to a filament circuit, the filament itself has a very low resistance. So I suppose you could argue that that use of this capacitor is in a low impedance circuit. A low impedance circuit means that a weak capacitor here will have a voltage drop across it. Now, you don't want that. Kind of a silly statement. All weak capacitors are going to have voltage drops across them that you don't want. Now the third element in here is in a very different place. A plate circuit, which I'm pretty sure is certainly high impedance compared to the heater circuit. So there the capacitor is working against high impedance. Because I'm so stupid, I have to do this right in front of my face to make this work. So imitating the filament circuit would mean having the capacitor work against low impedance. So I'm hooking up the low impedance resistor here. Boy, I don't know if this is even a valid thing at all, but so if this is an indication of what happens in the filament circuit, if this is what I've really got here, I could set this up right on the actual, I will set this up right on the capacitor somehow. I'll figure that out right on the real one somehow. But for now, low impedance results in the capacitor impedance being high or relatively high, you need a big capacitor in this spot. That's what this is telling me. I'm using it's supposed to be a 0.25. I got a 1 microfarad in here. The impedance of the heaters, how many ohms can that be? It can't be much different than this resistor, really. And so the objective, though, of this capacitor is not to work it down at this low end here. The real purpose is to work in the AM band. That's what I would think. So that would be from about 500 kilohertz to 1.5 kilohertz. So if I want to get that on the screen, did I say kilohertz? Yeah, 500 kilohertz up to 1.5 megahertz. That's what I wanted to say. So in this case, low impedance, the frequencies we're worried about, come on, 500 kilohertz. So if this is a megahertz, then this is 100 kilohertz here, and 200, 300, 400, 500 kilohertz way out here. So I would say there's no question the capacitor can work here. All the way out to, so now this is now 5 megahertz out here. This is 2.5. So 2 would be about here, somewhere in here, and look, it's working great. And if I lower this resistor even more, I think we might find out it's not so great. So this is the high resistor now. That funny little divot is there again. I wonder what that is. So, with either high or low resistance, you still get out to, this is 5, so this is 2.5. You still get out around 2, and most of it is dropping on the resistor. This is encouraging me to go ahead and put the electrolytic capacitors in. Now they're bigger. They're 4 times bigger. Is that a problem? I don't think so. I think they picked 0.25 because that was the smallest they dare go in the design of this radio. Look, 0.25 is already this big. If they wanted to go bigger, like a 0.5, maybe the engineers or designers would have been happier with a 0.5, but now you're talking about a can that's just that much bigger. So of course they're going to put in the least they can get away with. That also means it's close to the line in terms of aging. It doesn't have far to age before its age can cause problems, or its deterioration can cause problems. There's no headroom. Headroom would be the right word for it. So I'm justifying to myself putting in electrolytic capacitors here. And pretty sure in the heater circuit it shouldn't be a problem. Now what about the other circuit? The plate circuit. The plate circuit, I don't see that would be a problem either. Now how can I go about doing this in such a way that if I want to abandon what I'm doing, I can just kind of walk away from it? I haven't made too many changes to the radio. One is I can parallel them in, but that leaves these things. We never did a leakage test on this. Let's do a leakage test. It's not like I've got room in my head for more confusion. So let's do that. Let's bring on some more confusion here. Confused about which way to turn. Yeah, here we go. I have to use long leads. The capacitor is quite large though, so I don't think the long leads will hurt. I'm going to test this in the radio, but I did pull all the tubes out and I pulled the big plug out, and that makes me think that the capacitor is open circuit. So we'll put one on the ground. Let's just make absolutely sure this is not, no, it can't be plugged in. Let's just double up my safety there. One on the ground. Don't know which one is which in here, so we'll just pick one. Eeny, meeny, miny, mo. That's the one that's going to go. Now, what happens on the tester here? We're set to non-electrolytic. 50 volts, even though it says 25. Eye is open. Now, am I about to blast my oscilloscope or something? No. No, I can't do any harm. So I'm going to hit it with 50 volts and see what happens here. Watch the eye. So at 50 volts, the eye closes and doesn't come anywhere near opening. So now that's either because this test is bogus, the capacitor is actually in a circuit that's causing this, or this capacitor is so leaky it may as well be considered a resistor. I'm going to try another leg. See if we get the same result. Exactly the same result. So it's either this thing's really bad, or the test is bogus. I'm going to go for the test is probably bogus. Here we go. So all three of them show among the worst leakage I've ever measured. It really doesn't help me feel good about that test. If I'm going to replace it, then I'm not going to leave it in the circuit and parallel it. I'm going to actually replace it. And I'm going to want to separate these leads off of here. Let's take a closer look at it. Good deal. This is kind of a little ugly. So, you know, because these are terminals on a fixed thing, these terminals are rigid. When I cut them away and start sticking little capacitors, I'm going to have another floaty deal. Not so good. Not so good to have. So I could cut away one of these and then test with the terminal free, and to make an absolutely true test at that point. And then I could reattach the terminal if I wished afterwards. There's pretty darn stiff, but I think there's enough wire here to I could do something in there. Which one would I cut off? Which one of these is most interesting to test? Which one's the easiest one to cut off? Well, it's either this one or this one. Can I at least almost look like you could solder them up and pull them off? So this looks like a squeeze down, and this looks like a squeeze down tabs. So it looks like a squeeze down here on the wires and squeeze down here on this terminal. I don't know. No, I don't think I think it's an easy matter to just melt this up and then pull them out. I'd be driving the heat right inside this thing too. I think it's just a big honking pair of cutters and whack, off it comes. Everybody in agreement with that assessment? What a terrible focus on this camera. Let me just see if I can fix that. Sometimes I can, and sometimes I can't. No, can't do it. I won't explain why, but I cannot affect the focus on that camera, unfortunately. So I'm just gonna burst off one of these. Where should I cut it? Right here. It's a test of my strength. I passed the test. Wow, those are as stiff as can be. Holy smokes, much stiffer than I thought. So there can be a separation there. Just take a little piece of paper. Make sure they're not touching. Okay, now we're going to test. I'm going to repeat that capacitor test. to this now free terminal? I will find out. Well, we're going to get more information whether we're actually finding out something. Okay, that's good. Once again, 50 volts on the capacitor. So a good capacitor, even electrolytic one, these will slam closed and then they'll drift open. Let's hold this for a while. It's taking a little bit of time to charge up. No, it's not. It's not charging up. Any good capacitor, this thing would be open by now for sure. I'm going to put it on an electrolytic. Yeah, look at that. Now, is that capacitor electrolytic by some chance? I really don't think so. If it were electrolytic at that size, it would be much larger value, I'm pretty sure. Much larger. The parts list would also probably say if it was electrolytic. And are there any electrolytic capacitors in this whole thing? I don't think so. I think that's why that condenser can over there, which has now been removed from service, is that size. That's how big you need to make capacitors to achieve 2 or 3 microfarads non-electrolytically. Now you saw the tiny ones I put in to replace it. The same sort of thing's going to happen here. Okay, so upshot of all this is capacitor's bad, something must be done. Don't have the proper exact replacement or matching type right now. Only have electrolytic. And put in electrolytic capacitors, check and see what happens. Just have to figure out how to stabilize these. These are pretty stiff to begin with here. I'm not really ready to go anywhere. I can also cut them away, and this can come out if we want to get rid of it. The can's riveted in, so it's not coming out. I don't want to mess around with rivets. It's really a terrible focus on this camera. So if I replace them all at the same time, or do them separately, or I should replace them all just because, and then afterwards turn the set on. Now if for some reason these things are not doing their job despite all this monkeying around I've done, then I have an alternative to put a smaller non-electrolytic capacitor across the electrolytic ones to give the proper higher frequency response. I think that's the whole deal. Okay, that's it. That's the end of the thinking. Now it's time for the action. Is it thinking or is it stinking? Is it stinking thinking? I don't know. Just trying my best. So I'm going to stick 3 capacitors in there and fire this guy up. Okay, it's amazing how little I can go forward before I feel somewhat paralyzed again. Let's just take a look at the situation here. This is a 4-pin tube socket with 1, 2, 3, 4, 5, 6 terminals on it. What? Here's one over here. 4 pins, 1, 2, 3, 4, 5, 6 terminals with 2 wires disappearing through a hole here. What's going on? 1, 2, 3, 4, 5, 6. So something going on here with these sockets. Right. and what it is, I don't know right now. What are they doing with these sockets? Okay, and other things come into focus here. Some of these terminals are bent back so far that they would contact the plate here, and what I've noticed is they have a paper surround. I believe it's paper. That's very odd. It doesn't I thought it wrapped under, but it doesn't. It's just a ring. That's it. It's not. It's shaped. It's got a flat side here. Boy, that's really. Just never seen anything like that before. Doesn't explain why there's so many terminals yet. Okay, well, I keep the camera rolling here. I'm gonna poke around with my own meter. And obviously, there really can only be 4 real terminals on a 4-pin tube. Sit right there. So some of these terminals must be just connected together. Must be some kind of convenience for the radio manufacturer, giving him more terminals to make connections at. Okay, so we'll start right here. Just check it first, Jim. Okay. So this is a wide one, and this is a thin one. No, they don't seem to be interconnected. Now there's wires on a lot of these, so I could end up with some kind of ohm reading there that so if we look in this part here of this tube, can you see that? There's one terminal all by itself. There's nothing in here, nothing here. So this terminal must be going to this pin. That's a wide terminal. Maybe the wide terminals go to the pins. Maybe that's the rule, because there's a wide one here, but it's got nothing connected to it. Oh, jumper. What is going on? Thought I saw that jump. Jump like a capacitor. Well, I'm really being psychologically damaged today. This is really hurting my little brain. So the terminal that's connected to the pin is not connected to anything else. Is it connected to the chassis? Yeah, okay. We're getting somewhere. Maybe these are all connected to the chassis. Let's try this one. Well, that would be crazy, wouldn't it? This one pin might be connected to the chassis. How does it get connected to the chassis? Where's that connection? It's not up here. Let's see, another tube in the same situation as this one over here. It's got what looks like a pin contact with nothing connected to it. This is just the craziest stuff. I'm sure I got it there. Yeah, so that's going there. Is it also going to the ground? Yes, it is. So they aren't connecting this up because they've connected it to ground probably on the other side. It's connected to ground because this is the grid, I believe. Take that back. I don't know what it is. Let's leave it at that. So what are these guys? These pins here. Well, what are they hooked up to? Or these are spare connecting pins. But they only got one wire coming to them. They must be going somewhere. Meter. So going to each other. Zero. 5. Okay, well, this isn't coming clear to me exactly what's going on here, so I'm going to stop for a bit and do a little research and try to clarify why these 4-pin tubes have 9-pin sockets or 82-pin sockets in them. Some shorted to ground and others, who knows what's going on here. I'll figure it out. Okay, unfortunately I went through a whole speech about this and realized I didn't record it. So here we go again. So what now? I'm not even sure where I'm starting from. Oh my gosh. So we know this part of the 3-part capacitor is under DC pressure. So I can put this in a polarized electrolytic capacitor, put it in correct, no problem. These guys have AC across them, but it's a very low voltage, just a volt. So what can a volt do in reverse on a little electrolytic capacitor? I don't think it can do much to it. I don't think there's a fear here. There's something else I want to check. Oh my gosh. Okay, I checked it. So this is a volume control for the radio, obviously, because it's a potentiometer on the antenna. There's another one in here, right here. This is right in this circuit. So my question is, how do you control the volume on the record player? I thought this was going to do it. It's over here. So this volume control is a weird one because it's like a parasitic coil on this transformer, just killing it when you bring this close to ground. Is that right? No, when you move the slider towards this end of the resistor, you're pretty much putting a short across this. You're sucking the life out of this guy. Now look how you control the record volume. It has its own volume control, and it must be in the record player. So again, what's coming here is heading towards an amplifier that's essentially wide open. Yeehaw! If you got any problems here, it's going to come screaming out of the speaker. So we're probably seeing earlier versions of volume control solutions that each one of them had problems. And they hadn't quite got the whole thing sorted out yet, how to do it. They're still stuck doing a resistor on the antenna. There's no automatic volume control in here, unless I've really missed something. And consequently, I'm now looking to see if I'm sure that's the case. No, there's no volume control. These are not remote cutoff tubes. I don't think they just can't do it. You can't vary the bias on these and get any kind of volume control, and there's no way to vary the bias anyway on these guys. So consequently, you have to control the input level into the amplifier here. So you've got to kill the signal coming in from the antenna to keep this from being overloaded. And then further, after a couple of amplifications, it looks like you need to kill it again. Here. This almost looks like an afterthought. Like they found out this wasn't enough. Curious, never seen anything like that before, anywhere before. Never seen it since either. Okay, that's babbling enough. Was there anything else I had spotted on here that I babbled about? I don't think so. I think I'm pretty much convinced myself to go ahead and replace these capacitors with electrolytic ones. That's what this has all been about. And if the worst case, I'll just change them again. I'll order some and change them again. Okay, I'm going to get on with installing them, and then we'll see what happens to the radio. Okay, so I've got this guy on. Negative to ground, positive to this terminal. There's no chance of a short happening with the old terminals. They're all very clear. This guy is soldered. Sure. This guy, as bad as it looks, he is soldered in there. These things aren't going anywhere. There's nothing down there for them to short to. They're kind of actually protected in that little spot there. 3 done. I think it's time to test this radio. Okay, let's do it. Okay, just popping in the tubes. Bearing in mind this is, operating this radio without this top panel. Could be some kind of problem with that. I think I've done this once already, haven't I? It didn't really cause a problem. We set here. So we're hooked up to the loop antenna, and this guy's doing nothing. Let me just make sure there's no output there. Big plug in, power cord connected but not plugged in here. Okay, power off. There we go. Now, okay, so this is switched on. Speaker's plugged in. Everybody stand back a little ways. Shield your eyes. So what'll happen here is these lights are going to come on as usual, and who knows? Let's watch and see, and we even talk. Oh, what lights? Those lights. Something bad could happen. Now these capacitors could explode. Then again, maybe not. Okay, so I have it on the dim lights, as you can see. So it's 80, almost 90 volts reaching here. You can almost read it. Let's just check the volume here. Volume was full, absolutely no sound. That's not very good. We're going to give it full power now. Here we go. Shield your eyes. It's only one of these capacitors that's being subjected to a significant DC voltage. So we expect one bang, not three. Okay, radio, come on. Turn up the volume. She's dead, Jim. She's gone totally dead. This is not what I wanted. Okay, what could be wrong? Antenna could be off. No. Tubes are lit. Are they? Could have a tube failure at any point in this process here. Tubes are all lit. There's no excuse here except for the work I did. I hear a little bit coming out of there. Could it be the antenna is really poorly tuned? I don't think so. Let's tune the radio here. Come on. I got the volume turned up or turned down. I'm sure I had it turned up. There's something crackling there. Something there. Let me check the antenna. Come on, little radio. Have I messed it up? Did I switch it to phono at some point without realizing it? I don't know how that would happen. Well, let's switch it to phono. Big pop. Touch the input. Not very reassuring at all. Maybe something better here. That one's grounded. This one is the... Oh! Here a little bit. Turn it up. Oh, this volume doesn't affect that. That is wide open from here. So I haven't necessarily put the tubes in the same order. There may be a bad tube here, which was in a good place before, and now it's in a bad place. What else have I done here that I've kind of forgotten about? This is not the result I wanted, that's for sure. Give me another prod here. So we're going to tap around the detector tube and see what kind of noises we can get out of it. How about nothing? Nothing. Still on phono. Duh. Radio. Come on, somebody's got to make some noise here. It's plugged in. Well, if it wasn't plugged in, this thing wouldn't light up at all. This is the primary terminals here. She's gone dead. Dead to the world. Plug in the plug all the way. Sure looks like it. She's in all the way, all right. Well, it's another fine mess I've gotten myself into. You know, the easy conclusion is these capacitors are causing this. But I can't explain that at all. I can't imagine why these would. Deaden out the radio. There's just no reason for that. Let's try injecting signals along the way here. Just using this. Back here, you should be able to hear it. Somewhere. Nothing. We're running with 121 volts. Okay, let's come up a little closer. Wasn't this the last one before the detector? I've already touched the detector stuff. Didn't make any noises. Why is it gone? Totally dead. That's a good question, Jim. Usually in an operating tube device, when you wiggle tubes, you get a little crackling. It's a, you know, poor man's signal injection. So I can hear that. Okay, that's interesting. I tap this tube, I can hear it in the speaker. So why is it touching the grid didn't do anything? Where is the grid? Grid, probably this with the capacitor and resistor. This must be the grid. Oh yeah. Okay, and that connects to this coil. And this coil is part of the connection down there that I fooled with. Another part comes over here. Well, I'm gonna have to leave it like this today. That's the end of the journey for today. Tomorrow I will investigate what I've done here. I'm sure it's not the end of the world. Anyway, well, thanks a lot for watching, and it's gardening from here. See ya.